think, yeah, hopefully you can see it.
I exist. You're welcome.
All right. So I've kind of already introduced you guys, everyone. This is Topher. Like I said, Topher is a genius. So don't let him say otherwise. But yeah, he has agreed to come, like I said, talk to you guys about meteorites. And we are extremely lucky to be able to have him. He's carved out time in his day to talk to you guys. So please give your undivided attention. Topher, I'll let you take it from here, dude.
Awesome. Hey, guys. Thanks a lot. I really appreciate this. This is kind of exciting here. Let me see if I can get my screen share working. Hopefully, yeah, now you can see that, right?
Yeah.
Okay. Let me remove this. Well, I don't know how much you guys know about meteorites and the science and everything behind them, but I am fascinated by meteorites and everything from space. So as Beau mentioned, my name is Topher. I run a company called Topherspin Meteorites. So I actually got into meteorites about almost 4 years ago, and I just fell in love with the science of it, the rarity of them. And since then, I've actually joined a lot of professional organizations. So you'll see here, I'm a Meteorite Club member. I'm a Pioneer member, and I'm also on the board of directors for their communications. I'm a member of the IMCA, which is International Meteorite Collectors Association. And the reason Beau reaches out to me is because I do a lot of education work on YouTube as well. So I'm a member of the Meteorite Education and Trade Society, as well as the Global Meteorite Association. So with all those associations, I'm able to connect with people and get a lot of good information and then disseminate that information. So have any of you guys heard of Chelyabinks before?
I don't think I have.
Well, Chelyabinks is a massive meteor that exploded over Russia in 2013. That should work a lot better now. Okay.
Yeah.
Okay. So there's a bunch of words that I'm going to use, and you're probably going to hear and are familiar with some of them, but maybe you don't know the exact definition and how they differ from each other. So out in space, you have this huge rock floating around, and that's called an asteroid. And if you have a smaller one, it's called a meteoroid. Now, every once in a while, at predictable times, we have meteor showers, like the Leonids, the Geminids, and they're planned out, and we always know they're going to happen. And that's because we are going through the tail of a comet. So a comet has an orbit, and it has a bunch of debris behind it. And as it zooms around in its orbit, it pulls that debris along with it. So it actually has a bunch of debris in its orbit. And every time Earth passes through that debris field, we get tiny little bits of sand and tiny little bits of cosmic dust. And I am losing my screen again. But let me see here. So many windows. There we go. Okay. So those are planned and those are scheduled. We know when they're going to happen. And it never leaves enough material to have rocks on the ground. It's literally just tiny little bits of sand. Well, every once in a while, we have a big enough rock that enters our atmosphere. Usually it comes from between Mars and Jupiter. There's an asteroid belt there, and they bump into each other, maybe get knocked off course and come towards Earth. Well, they get attracted by Earth's gravity and they start entering Earth's atmosphere. And the good thing about that is what the Earth's atmosphere does. It saves us, it protects us. It does exactly what it did with the Chelyabinks meteorite that we're looking at there. You see it actually disrupting, and as it hits the thick air of the atmosphere, it just explodes. So what you're actually seeing there is a meteor. That's the event. Anything that happens in Earth's atmosphere is a meteor. That's why when you turn on TV, you watch your meteorologist give you your weather, because they're concerned about Earth's atmosphere. Well, I'm not really concerned about Earth's atmosphere. I'm worried about rocks on the ground. So once that meteor, if it does survive and hit the ground, now it becomes a meteorite. And that's kind of, well, this right here is one of the newest irons found in Sweden. They had a video, they tracked it down, and they were able to find it. So here's a really cool video of a meteor that actually landed in the UK. And it landed in the Wellcock's driveway, and I actually had a chance to interview them. So pretty interesting story. Now, what exactly are we talking about when we talk about meteorites, and where do they come from? How are they classified? How are they different? What are the types of them? There's so many questions. Well, if you think about early space, before planets, before everything, basically, before our sun, you have this cosmic dust floating around that is statically charged and attracted to each other. And then once it starts getting attracted to each other, more pieces glob on and it starts getting bigger and bigger. And once it gets big enough, you see the second picture here, how it has kind of like a glowing red center, a tiny bit. What you're actually getting there over time is a bunch of materials that congeal together, and they have radioactive breakdown. And as they break down radioactively, that gives off heat. That heat penetrates the entire material and kind of melts and loosens up everything. So all the heavy stuff goes to the center, all the metals that are now liquefied, and all of the lighter stuff, the rocks, all float up to the outside. So that's kind of what you see here in this final picture. Kind of probably reminds you of a section that you've seen of Earth, where we have a liquid metal core, a large mantle, and then a thin crust on the outside. So basically, if you start over here and go this way, you're looking at the birth of a planet. Well, sometimes planets don't make it. They get smashed, they get hit, they get obliterated out there in space. And lucky for us when that happens, because that's what we get is meteorites here on Earth. So this first type, there's three main types of meteorites that are out. There's a bunch of classes of meteorites. Just to show you how crazy it is, this is what the chart looks like, okay? We're not gonna get into that. We're gonna deal with what the majority of meteorites are. Of all meteorites, about 94% of meteorites fall in these two columns right here. So of the 100 that fall on Earth, 94 of them will fall in one of these columns. 85 will fall in this column. And if you look over here, these are the most common meteorites we have. The ordinary chondrites, you'll see, represent a massive amount of meteorites. Then the next large group would be irons and stony irons. So I'll show you where those come from. When the debris, the meteoroid or planetesimal at this point, is not even formed, that's when you have chondritic stony meteorites. Those are the chondrites, those are stony meteorites, and that's really, it looks like a stone with metal in it. As it gets heated up and gets bigger, we get what we call differentiation. So instead of all the metal being mixed in the rock, now it's getting heated and pulled towards the center, and the rock is going towards the outside, and so it's differentiating, it's coming apart. So that's what we have here. Imagine if something was huge enough to smack the Earth, if this is the Earth, something came along and smacked the Earth and ripped it open enough to spill our liquid metal core out into the coldness of space, that would produce iron meteors, iron asteroids or iron material, versus the outside of the planet and the core, I'm sorry, the mantle is going to be more of the stony iron, of the stony meteorites material. But there's a really, really super sweet spot. It represents about a 4% barrier, a 4% little part of the cross section here, where the liquid metal of the core and the stone, the silicates from the mantle and crust mix together in what's called the core mantle barrier. And when that happens, you get these very beautiful meteorites called pallasites. They are stony irons. So you have the stonies, the irons, the stony irons, and then once the planetesimal is actually completely differentiated, you get achondritic. So we have chondrites here and goes all the way to achondrites. And I'll explain to you a little bit what that is. I don't want to get too far into the science, but I do want to get enough science to get your minds wet. So we looked over here at most of the meteorites you're going to find are stonies. That goes to reason because not every planetesimal is going to grow to the size where it can be differentiated. Not everything's going to last that long. And so most of the items that we receive here on Earth from outer space are chondrites, and they fall into this category here: L chondrites, LL chondrites, and H chondrites. And basically, that's just a measurement of how much metal is in the meteorite. And depending on the percentage of metal, it falls into a different group, different class. So then we talked about the the irons being from the center. Excuse me. We talked about the irons being from the center of the planetesimal that was destroyed. So here's the breakdown of different iron classifications. And the way those are kind of broken down into families, because all the study of meteorites, meteoriticists, want to break down everything and have it fall into a category, into a classification. So we want to be able to say that it's not only an iron, but it's a 3E iron. And what that means is, just like we talked about the metal concentration telling you what class the chondrite is, when you go to iron, you're looking at concentrations of germanium and gallium, and you're comparing those minerals to overall composition of the material. And if everything lines up, then you know exactly what family that meteorite falls into. So there are all different kinds of ways to recognize meteorites, and you'll be surprised how many people think they have meteorites when they don't. Meteorites are more rare than diamonds. Like, you're more likely to go outside and find a diamond in your driveway than find a meteorite on your 2-acre property. It's just the number I've heard is 1 event per 10,000 years per square kilometer. So if you have a kilometer of land, there'll be 1 meteoritic event every 10,000 years. Now that might be 1 little pebble falling, or it may be a Chelyabinsk event that rained down hundreds of thousands of pieces. But if you look here at this, giving you some examples of fusion crust. Now, fusion crust is created during the ablation period, and that's when it's a meteor, when it's coming through the atmosphere and it's pushing against through this thick air. It's going, 30 to 40, 70,000 miles an hour. And all of a sudden it hits Earth's atmosphere and starts slowing down. And it has a bunch. So basically, imagine it's coming through the air, and all the air is just piled up in front of it because it has to push its way through the air. But after it's already gone through the air, there's nothing behind it, like a little vacuum. There's a low pressure system behind the meteor, and it's compressing all the air in front of the meteor. So you have a high pressure in front and a low pressure behind, and eventually it pulls so much that the meteor bolides and explodes. So that's why I call my YouTube channel the Knowledge Bolide, because I like to explode knowledge all over you. So that's an idea of why meteorites explode or bolide. This is the fusion crust that's created by that very short ablation process. The ablation process is the heat that's generated as it comes through the atmosphere. You'll see this one is a lot more weathered. You can see that the fusion crust is still present, but you can obviously see the matrix, the internal of the meteorite. Whereas this one is super fresh. You can literally see the bubbles and everything inside the fusion crust. What's also interesting about this is each meteorite tells a story. So if you're looking at this, while this was all liquid and flaming, something hit it right there. You see that? So every time you look at a meteorite, it tells you a story of its creation, its entry into our Earth, and also how long it's been on Earth. And talking about entering Earth, there's lots of features that we look for on meteorites that explain how it entered our atmosphere, how it came to be. If you look at, these are just some beautiful, beautiful pictures. This is what we call a nose cone. This is an oriented meteorite. You can obviously see that it was flying in this direction, and you can quite honestly see these lines. We call these flow lines in the fusion crust. It's literally just dripping liquid rock back as it's flying through the atmosphere. And because there's a low pressure system in the back, you get this flat side. So here's a meteor, an oriented meteorite looking directly down on top of it as if it was falling from the sky at you. You can see all the flow lines lead outward from the very center. Now here's what the backside of a oriented meteorite looks like when you're super lucky. This is the bottom. So we're looking at like this side. It's not the same meteorite, but we're looking at the backside of the meteorite right now. So that's what this is. As the fusion crust is liquefying and rolling off here and flying through space or our atmosphere, the liquid fusion crust lips over and gets stuck on the back of the rock. And that's what you're seeing right here. This beautifully sexy, beautiful line right here is where that fusion crust lipped over the rock and was frozen solid in time. So it really captures the dynamic flight of the meteorite as it enters our atmosphere. I talked about classifications of chondrites. So what we're looking at here are some chondrites. These are stony meteorites. And if you look here, you'll see that there is the total metal percentages over here. So and these are wrong. The H should be higher than that. Actually, the LL should be lower. LL has the least metal, L has a moderate amount of metal, and then H, heavy metal. As a material is created, it is as a meteorite conglomerates and congeals, it has these perfect spherical chondrules and a perfect rating for a untouched, unchanged, unmetamorphosized, meaning no water, no heat. It hasn't been changed since it was 4.67 billion years old. You have these beautiful little chondrules in here. And when they're absolutely perfect and untouched by heat, you get a 3.0. That's the most perfect you can get. So this is very, very what we call primitive material. It's unchanged. It's LL, it has low metal. It's a 3.15. So it's been barely touched by heat and very rarely altered. So that's why you can see a lot of the chondrules in there. Now, if we move to look at the buzzard coulee, that's a witnessed fall up in Canada. You can see that there's more chondrules in there, but they're bigger. They're not as well defined. That's why it has a 4. It has more metal, so it has an H. You can definitely see there's a lot more metal in El Hamami, but you still see some chondrules in there. So it's an H5. Now here's one that's witnessed Venialis. It fell in Cuba a few years ago. And this one has a heavy shock rating. You see the shock rating of 3. It's higher than 2 and 2 here. That's why it's all broken up and brecciated. This rock experienced a violent lifetime while it was in outer space. So here are some more looks at what we are looking for when we cut open a rock to see if it's a meteorite. We're looking for this, this metal being dispersed throughout the material. We're looking for brecciation. Brecciation is basically many rocks that have been basically become one. They've been heated and smashed due to one event, and now they're one rock. So you can look in here and see there's many different kinds of rocks. There's a white one, there's a brown one, there's a tan one, and then you have this melted material all around it. Talking about melt, here's an impact melt. When things are in outer space and they hit each other, it generates a lot of heat and a lot of energy. That energy can't radiate into space. There's nothing to absorb it. So the meteor at this point, well, actually the asteroid, absorbs all that energy, and all that energy has to go somewhere. Well, sometimes it turns into heat. And if you can see on this melt here, you have a bunch of melted material in between other non-melted material. And then over here is another example of a pretty, what we call primitive material, meaning a 3 something, very unchanged. Now, when we get into irons, it gets even more beautiful, but a lot more scientifically complicated. So here are some. I don't expect you to memorize all this, but just to show you some examples of what a iron meteorite will look like on the interior. Does anyone know what this pattern is called? It's German. I didn't think so. It's called the, what's that?
I said no.
Okay, it is called the Widmanstätten pattern. Or you can
What?
say Widmanstätten. What we're basically looking at
Sounds like a
here,
made-up word, but okay.
it's
Makes
not a
sense.
made-up word.
I know it's
Trust me.
German.
You can Google it if you can spell it. The Widmanstätten pattern basically is created through eons of time. A meteorite cools extremely, an asteroid cools extremely slowly in space. We're talking about 1 degree per 1,000 years. It's a very slow rate. Well, when you've ever seen someone forging metal and they're trying to make a sword or a tool and they're trying to mix two metals together, what do? They stick it in an oven, get it glowing red hot, and then beat the heck out of it, stick it back in there and fold it upon itself and hit it and beat it and heat it. Well, in outer space, these metals are liquid and they cool slowly. Well, while that happens, the metal goes through different phases. When it's a pure liquid, the nickel and the iron get along just fine. They're good friends and they love each other. Well, the colder or the cooler the material gets, the harder and more solid the metal gets, and it goes through different phases. As it goes through phases, it says, you know what? at this temperature, I am this solid and I can only carry 42% of that. So it kicks out the rest. Then it cools down even more over another 100,000 million years, billion years. Cools down some more. Now it gets the phase in its hard metal where it can only hold 3% of that material. So it's constantly pushing and pushing and pushing. So what you're actually seeing here is the separation of nickel and iron with the camosite bands going between them. So this cannot be faked by men. This cannot be man-made. This is something that exists only in nature through the eons of time that's used to create it. And some of the patterns are just absolutely gorgeous, and you can actually identify the meteorite through looking at the pattern. And then obviously there's a bunch of minerals that go in there chemically. The most beautiful meteorites, if you ask my wife, are the pallasites. They're also kind of the very, very rare and very expensive. So here are 3 pallasites. Now, if you remember, these contain not only the liquid metal, but the liquid silica. So these are about 50% metal and 50% rock. And that's where you get this beautiful translucency in these olivines here. So this is Brahin from Belarus. This is Esquel from Argentina, and Admire right here from the United States. This is the main mass to my official meteorite, NWA 13579, the odd numbered golden pallosite. And as you can see, it is beautiful nickel iron silicates here with beautiful olivines sticking out. This one I had officially classified, and that's the main mass to it. There's also other kinds of meteorites that we haven't discussed yet. These are the achondrites. We've talked about the chondrites, the stonies, the stony irons, and the irons. But now, once that planetesimal gets big enough and it gets differentiated, you can get achondrites. And that's where we get the moon from. So right here, this is 56 grams of the moon, and it's actually like the continent of Africa. Here is a 20-gram slice of the moon, and you can see it has anorthite. It has different minerals, different chemicals in it that we can identify and tell where on the moon it came from and a little bit of its history. Now, just like the moon, there's another big one out there that's differentiated that we have samples from that we know for sure came from Mars. So these are some Mars meteorites, and this is what Mars looks like up close. It's not red. The red on Mars is iron oxide that you see on the outside. It does have a very thin atmosphere, and because of that, the planet is kind of rusting. So here is a beautiful piece of Mars. Any one of you guys can buy it for $5,000. That's what I'm asking for it. You'll see it's oriented. There's the top of it, and the flow lines come over to the side, and there's the rollover lip that I talked about earlier. This is a super, super fresh piece of Mars. It has not been on the ground very long at all, and by that I mean maybe 100 to 200 years at most. I don't think much more than that. I'm kind of moving along, so I got 2 minutes, so I want to get done, but I have 2 or 3 more slides. So this is the official Bible of meteorites. It's the Meteorological Bulletin Database, and your teacher can show you how to find this, but this is where meteorites exist. If it's not printed here, it's not official and it doesn't exist. I want to take this chance to thank you for allowing me to talk to you guys. If you have any interest in what I've talked about, I really, really, really would love for you to search on YouTube for Topherspin Meteorites. This is the video well, I'm doing a video I'm very proud of right now, but my proudest video was with Dr. Lawrence Garvey. He is the curator of ASU's Center for Meteorite Studies. And he is just an amazing, passionate man, and just a great guy. So he actually allowed us virtually. I've been there before, but he did a 2-hour private tour inside the vault where he was running around grabbing samples for us, telling us stories, telling us history, giving us science. So I really recommend this video, and I do thank you for your time and attention, guys. If you want to be a baller, you got to get a meteorite. I'm just telling you right now.
Meteorite Mafia.
Yeah. There's a lot of people out there who believe that just because we tell them their rock is a rock and there's no meteorite value because it's not a meteorite, well, we're the Meteorite Mafia. We're trying to control the entire globe of meteorites, and it's just not true. So one of my buddies made that for me, just to. Well, in the middle picture there, I'm actually kissing the main mass to Barnstable. Barnstable is I think a 26-pound meteorite that my friend found. It is the largest meteorite ever found in Massachusetts, one of only 3 ever found. So I really appreciate your attention today. If you have any if you want any follow-up information, I'm easy to find online. If you just go to YouTube and look for Topherspin Meteorites, you'll find my channel. There's about 130 hours of educational material consumed every day. Every Wednesday, I have a virtual hangout, lasts for about 2 hours, and we just chat about meteorites. We do show and tell. We do all kinds of stuff. So I'll switch over to a camera like this and show off a beautiful piece of meteorite like this, where you can actually see its aerodynamic shape, where it hit the ground, scuff marks from the sand of where it impacted the ground. Here's the negative pressure side, and it also has.
You holding it?
Yep, and that is fusion crust right there. Here is another one. This one's officially classified. So if you look at this, you can see it has the fusion crust, some contraction cracks, a bunch of weathering on it, and then it's been cut, and I don't know if you guys can see the metal in there or not. Maybe it's too bright, but there you go. So that's a classified meteorite. And then I just wanted to bring this one out because I like touching this whenever possible. This is 43 grams of the planet Mars. So this is what Mars looks like right here. Have any of you guys ever seen Mars up close?
Nope.
No.
I've only seen a photo of it.
All right. Wait a second. Is that the piece of the ground?
Yep. There are a bunch of, most of the meteorites that we have come from the Northwest Africa region. And a lot in Chile and Argentina as well. The reason for that is it's really the only place on Earth that's friendly to meteorites. If it falls in a lake, or if it falls in a city, if it falls in a swamp, if it falls in a rainforest, if it falls on top of mountains, in a river, deep, there's so many places, all the oceans, all the lakes, that meteorites will not last. Anywhere where there's like farmland, or they're building city and they're just going to pave over it, all the meteorites are lost. So basically, what you're looking for is an environment that will safeguard and save the meteorite. So once it lands, let's say in the hot desert of Africa, and the sand dunes move and they cover it up and they protect it, they insulate it, it can sit there for 10,000, 20,000 years untouched. And then if the sand dunes move again, it could be revealed and be almost as fresh as the day it fell. Are there any other questions?
No, I don't think so.
Awesome. All right, guys. Well,
Good
I
luck.
sure appreciate your interest in meteorites and in space exploration. You can always contact me through your teacher. I appreciate your time today, guys.
Okay, bye.
Thank you.
Thanks, guys.